Hi, welcome to another session of Circuits and Networks. In today's class 10 under two-port networks, we'll see the problem and solutions using dependent sources. Now here you can see we have current dependent current sources in both these two problems. So how to solve current dependent current source problems? That is the main concern about this particular class. So we'll start off with the first problem where we need to find out the transmission line parameters, that is ABCD parameters, the H parameters, which are also known as hybrid parameters, the admittance parameters known as Y parameters for the network shown in figure 1. So with the impedance parameters, I'll sort out the circuit. First I'll find out the impedance parameters. Then I'll convert the impedance parameters in terms of transmission line, hybrid and Y parameters. So we'll be obtaining ABCD, hybrid and Y parameters in terms of impedance parameters, and the results can be compared with the normal approach. So what we are doing, first we are going to open circuit the output port. The output port is this, where you have V2 and I2 it is flowing. So this we need to open circuit. When port 2 is open circuited, I2 will become as equal to 0. And this is how figure 1 changes to figure 1a. Here you can see V2 is the measurement across 3 and 2, whereas I1 is driving current for this closed circuit where you have input voltage. You have the drop across 1 ohm, you have the drop across 3 ohm in terms of I1 only. So what we are going to get when we are going to open circuit the output port, we are going to get V1 in terms of I1 and V2 in terms of I1. Hence we are going to obtain Z11 and Z21, right? So by clear inspection, when I'm going to apply KVL to this loop, I'll be having minus V1 plus 1 I1 plus 3 I1 equivalent to 0. Therefore, V1 be equal to 4 I1, and hence Z11 is equal to the ratio of V1 by I1 at I2 equivalent to 0, whose value is 4 ohms. Let us treat this equation as 1. Now, V2 is the measurement across 3 and 2. And what is the current which is flowing in 3 ohms? That is I1. What is the current which is flowing in 2 ohms? That is the dependent current source 0.9 I1. So it is flowing in this fashion. So naturally, the developed voltage will be across 2 ohms will be in this fashion. So you have minus over here, plus over here, because the current is flowing from higher to lower. By assuming that, we frame the drops across 3 ohm and 2 ohms in terms of I1 and 0.9 I1. And when we are going to apply the KVL to this particular loop, I'm going to get minus 3 I1. Then you have minus here, minus 2 times the current. The current here it is dependent current source, so 0.9 I1 plus V2 equivalent to 0, which will give you the value of V2 in terms of I1, that is 4.8, and hence Z21 will be equivalent to the ratio of output voltage by input current at output current is equivalent to 0, whose value is 4.8 ohms. So let me treat this equation as 2. Now what? I'm going to take the input port and I'll open circuit it. So I1 is equivalent to 0, and this is how figure 1 changes to figure 1b. Now when I1 is equivalent to 0, this dependent current source, whose value is I1 multiplied with 0.9. So when it becomes open circuit, I1 is 0, so it becomes 0. So 0 multiplied with 0.9, it becomes 0, and current source it is dependent. So that is why this is also open circuited. Hence, I will be left over with 3 and 2 connected to V2, and I2 is flowing into this circuit. So V1 is the measurement across 3 ohms, whose value will be equivalent to 3I2. Overall, V2 is equal to Z22 I2 and V1 is equal to Z12 I2. So V2 by I2 at input current is equal to 0 will be obtaining the value as 5 ohms, whereas V1 will be equivalent to 3I2. So Z12 will be equivalent to 3 ohms, and hence by framing equation 4, 3, 2 and 1, the Z parameters are obtained as 4, that is Z11, 3, Z12, 4.8, Z21, and 5, Z22. So once we are done with impedance parameters, we can convert the impedance parameters into transmission line parameters, the hybrid parameters, and Y parameters. So for that, I'm calculating first the delta Z, which is nothing but Z11, Z22 minus Z12 and Z21. With this, I'm going to get the value of delta Z, which will be equivalent to 20 minus 3 times 4.8, which will be giving the value as 28 by 5 or 5.6 as the value of delta Z. Now ABCD can be obtained with the help of Z parameters by this equation. So 1 by Z21 matrix Z11 delta Z1 and Z21, sorry, Z22. This we have already seen in our previous classes. We have seen also the derivations. So you can look into our two-port networks different classes, and there you can find the approach to convert one parameter in terms of other parameter. So directly now we are going to apply the formula. So Z21 is 4.8, Z11 is 4, Z22 is 5, 1 as it is, and delta Z we obtained as 5.6. So this is how the transmission line parameters are obtained from impedance parameters. Then H parameters is equal to 1 by Z22, delta Z, Z12 minus Z21 and 1. Also we have seen this derivation in our previous classes. So please check into my previous videos to obtain the one parameter in terms of other parameters, that is H parameters in terms of Z parameters. So here we are going to just substitute the values of impedance parameters, that is 1 by 5, Z22 value is 5, delta Z is 5.6, Z12 is 3, minus Z21 is minus 1.4, sorry 4.8, 1 as it is, and finally the Y parameters, that is the inverse of Z parameters, we are going to get the value as 1 by 5.6, 5, minus 3, minus 4.8 and 4. Now what we have to do is that you need to calculate all the parameters with normal approach, that is ABCD parameters, H parameters and Y parameters, and after obtaining the values of ABCD, H and Y parameters, compare the results what we have obtained using this conversion, and please answer me in the chat box whether you got the correct values or not. So treat this approach as a homework, and please comment in the chat box whether you're getting the same values or not. Okay, so let us go with another problem. In figure 2, you have again a current dependent current source. If at all you remember, in my class 9 we have seen the same problem, but the dependent current source here it was 3i2. So unlike that problem, in this problem it is 3i1. So that is the change made in this problem. Now if this is done, how to solve the Z parameters and Y parameters? In fact, you can find out the transmission line parameters and hybrid parameters by normal approach. And please answer in the chat box whether you are getting or whether you are able to solve these kind of problems or not. So let us go with the solution. So for impedance parameters, the normal approach is that we are going to take open output port and we are going to open circuit it. So when you are going to open circuit it, I2 will be equal to 0. So this is how figure 2 changes to figure 2a. Now I2 is 0, but V2 is a measurement across 2 ohms, that you need to remember. And it is also connected parallelly with 3i1. So what are the voltages across 2 ohms? The same voltage applicable to 3i1. Now I1 is flowing into the circuit. Now what the things we can do? So I'm going to take the help of KVL. So I'm going to apply loop current I1 in this first loop, second loop IX, third loop IY. In fact, IY is equal to 3I1, isn't it? Because here the loop current IY and the branch current 3I1 in this particular branch is one and the same. So IY is equal to 3I1. Okay. And when you're going to apply KVL to the loop 1, so minus V1 plus 1, I1 minus IX is equal to 0. So V1 is equal to I1 minus IX. This I'm treating as equation 1. Also, when I'm going to apply KVL to the loop 2, I'm going to get 1 IX minus I1 plus 2 IX plus 2 ix minus iy equal to 0. Now you have v1 is equal to i1 minus ix, and iy it is obtained as 3i1. So you can take the help of these two equations, substitute in this equation, so that I'm going to get ix is equal to 7 by 5 i1, and let me treat this equation as 2. Now I know what is iy and what is ix. The imaginary loop currents which I have taken, the original values of loop currents ix and iy is obtained in terms of i1 with equation of iy and with equation of ix. So with this, what we can do, we can get the uh, impedance parameters when output current is made equal to 0. So substituting equation 2 in equation 1, I'm going to get V1 is equal to minus 2 by 5 I1. In fact, Z11 is equal to minus 2 by 5 ohms. So let me treat this equation as 3. Also, V2 is a measurement across 2 ohms. So 2 ohms is having the loop currents impact as Ix and Iy. So V2 is equal to 2 times of Ix minus Iy that we have seen or we have observed from this particular loop analysis. So 2, we know what is Ix and Iy. So I'm substituting the value of Ix and Iy in terms of I1. So I'm going to get the value of V2 as minus 16 by 5 I1. In fact, Z21 is equal to minus 3.2 ohms. So we have obtained just the input impedance and the forward transfer impedance with the help of equation 3 and 4. Now, I'm going to take input port and make it to equivalent to 0. That is, current is made equivalent to 0. So this is how the figure 2 changes to figure 2b. Right? Now, what is this I2 dash? I2 dash is the current which is flowing in 2 ohms in series with 1 ohm. That you need to remember. You can easily find out the value of I2 dash with the help of current division rule. Well, let us see that how we are going to do this. So when 2 and 1 are in series, the entire combination, that is 3, is in parallel with 2. So it becomes 3 into 2 divided by 3 plus 2. So it becomes 6 by 5. In fact, V2 in terms of I2, I'm going to get as 6 by 5 ohms. Is this clear how we got Z22? Right? Now, what is V1? V1 is the voltage developed across 1 ohm. And what is the current which is flowing in 1 ohm? That is I2 dash. And what is I2 dash? I2 dash is nothing but the total current into opposite resistance divided by sum of this parallel resistance, that is 2 plus 1 plus 2, it becomes 5. So 1 multiplied with opposite resistance is 2, total current here it is I2 divided by 5. So that Z12 can be obtained as the ratio of input voltage to output current, where input current is equal to 0 as 2 by 5. So with this, we'll get Z parameters whose values are minus 0.4, 0.4, minus 3.2 and 1.2. I'm framing this equation as 7. Please remember this equation. Now I'm going to take another approach, that is obtaining Y parameters. For that, I'm going to short circuit the output port, and I1 can be obtained, which is equivalent to I1 minus IA. What is this IA? IA is the assumed loop current over here, and IB is the assumed loop current over here. So we are going to take loop 1 in I1 minus V1 plus 1, I1 minus IA equal to 0. With that, we are going to get the equation 9 as V1 equal to I1 minus IA. I hope you understood this equation. Now, when you talk about this loop and this loop, 3I1 is shared between IA and IB, and this becomes super mesh. So 1 and 2 are there. So I'll take dominating loop as IA. So you have 1 ohm here. So IA minus I1 multiplied with 1 plus 2 times of IA, and the circuit is closed like this, equivalent to 0. With this, the super mesh equation is framed so that I1 will be equivalent to 3IA, or in fact IA is equal to I1 by 3. So let us frame this equation as 10. Okay. With this 10 substituting in equation 9, I am going to get V1 is equal to 2 by 3 I1. In fact, Y11 will be equivalent to I1 by V1 at V2 equal to 0, whose value is 3 by 2 Siemens. So let me treat this equation as 11. Then you have the supermesh equation, that is 3I1 is equivalent to IA minus IB, or IA minus IB equal to 3I1. With this, I am going to substitute the values of IA, which is nothing but I1 by 3, minus IB is equal to 3I1. In fact, IB is framed in terms of I1. But from equation 11, I1 is equal to 3V1 by 2. So with this, 8I1 by 3, because the assumed current and the actual current are in opposite directions. So I2 will be equivalent to 8I1 by 3. In fact, when you're going to substitute this I1, you observe here IB is nothing but equivalent to minus I2. This is the catch over here. Don't get confused over this equation 12. IB is equivalent to minus I2. That's why we got 8I1 by 3 is equal to I2. And just I1 we have replaced with 3V1 by 2, so that I can get the values of I2 divided by V1, so that Y21 will be equivalent to 4 Siemens. You have to be careful while applying the values. That's why we have framed so many equations as 9, 10, 11, 12, so that Y21 will be equivalent to 4 Siemens, and this one treating as equation 13. I hope you understood this approach. Okay. Now when input port is shorted, the figure 2 changes to figure 2D like this, because this one is only it is getting shorted. You have 2 and 2 which are in parallel. In fact, this 2 parallel combination leads to the value as 1 ohm. But before doing that, you remember I2 it is flowing over here, and 3I1 it is a dependent current source. So though V1 value is equivalent to 0, I1 is not 0. So that is why we have to consider this 3I1 strongly over this particular point. For this, I can apply KCL at this particular node. So that V2 it is parallel to 3I1, V2 is parallel to 2. In fact, when I'm going to apply KCL, assuming this point to get higher potential, so V2 by 2 is one branch current, V2 by 2 is another branch current, 3I2 it is a dependent, 3I1 it is a dependent current source which is leaving the node, and I2 it is coming towards the node. So I can frame the equation as V2 by 2 plus V2 by 2 minus I2 plus 3I1 equivalent to 0, where I1 is equivalent to minus V2 by 2, because the direction of I1 it is in this direction, and what we are assuming this point to be at higher potential. So V2 by 2 is equal to minus I1. So I hope you understood this step. Anyway, first we have applied KCL at this particular node and we framed this equation. Now V2, because this V2 by 2, V2 by changes to V2 minus I2 plus 3I1 equivalent to 0. I am treating this equation as 14. And I1, as I told you, it is nothing but minus V2 by 2. So with this, I am going to get the value of Y12, whose immediate value is minus 1 by 2 Siemens. And I am going to employ this equation 15 in equation 14 to get V2 in terms of I2. So V2 is equal to minus 2I2, so that Y22 is equal to I2 by V2 at V1 equal to 0, whose value is minus 1 by 2 Siemens. And hence, we frame several equations and we got all the admittance parameters. So the admittance parameters are obtained to be 3 by 2, that is Y11, minus 1 by 2, that is Y12, Y21, 4, Y22, minus 1 by 2. So here we don't have the reciprocity and symmetry conditions because the values are different. Why they are different? Because the problem is involved with dependent sources, especially dependent current source. Anyhow, let me determine the modulus of y, that is delta y is equal to whose value we are obtaining here as 5 by 4. So I can get impedance parameters from admittance parameters by taking inverse of this admittance parameters. So Z is equal to 1 by delta Y. This is Y22 minus Y12 minus Y21 and Y11. Just substitute the values. You can see delta Y is substituted as 5 by 4. Y22 is minus 1 by 2. Minus Y12 is nothing but 1 by 2. Minus Y21 is equal to minus 4. And Y11 is 3 by 2. Now we need to cross multiply all these values. So I'm going to get Z is equal to minus 0.4, that is Z11, 0.4, that is Z12, minus 3.2, that is Z21, and Z22 is equal to 1 by 1.2. So this equation what we have framed for Z parameters, it is quite similar to the values what we have obtained using normal Z parameters approach. So this is how you cross check, and this is how you employ the different techniques in order to obtain different parameters for given network. I hope in today's class 10 uh, you have got the idea how to solve a problem which are involved with dependent sources in multiple ways. So I hope you like this video. Please share among your friends, subscribe to this channel, and please press the bell icon for the future notifications. Thank you.